Luxembourg. I'm generally interested in building gene regulation networks, but today I decided to talk at a different side of my work, which has to do with the development of software. Once we come up with a new cool bioinformatic or biostatistical method, how do we disseminate it, how do we share the code, and make sure to engage the users in the best possible way. So, how not to share the code, and on Google Drive, Dropbox, and so forth, but perhaps use GitHub. GitHub because GitHub enables version control and collaborative and social coding. And so Arlab develops tools for the reconstruction of gene regulatory networks, and those are bipartite networks with proteins called transcription factors that regulate the expression of genes, and the disruption of gene expression often leads to disease such as cancer. We like to name our tools after animals, and the set of tools is called the network zoo, and this is work carried out with Tianhuang. So, and 4 months back, we reconstruct this type of networks for a population of samples. Lioness does it for only one sample. Condor and alpaca detect communities in gene regulation network. And monster and sambar allow to find missing edges in those networks and also estimate transition between the networks. So those tools are implemented in R, Python, MATLAB, and C, 7 tools and 17 implementations. So when I started, those tools were not in GitHub, they were on Google Drive and SourceForge and all. And even when they were on GitHub, they were not maintained, so which means a lot of them did not work. So what I did was to put them in one page and have them accessible for collaboration, so people who use them can actually create what's called pull requests to change the code in this tool. And the main feature of this is the website GitHub.io, and the main feature of integrating all the code in one place is enable continuous integration. Continuous integration is a set of tests that run every time a change happens in the code to make sure that the expected output is given. And then when you go to the GitHub page, you see build passing, which means the package is actually functional, it doesn't have any bugs. And this is possible through using third-party tools like Travis and Corbin. Also, we created the website for documentation to show how we can install, how we can contribute, and describe all the functions. And this is possible through a package called package.one for R and Docs for all the other languages. We also created tutorials in R Markdown, Jupyter Notebook, and MATLAB Landscape. And a website or a landing page where all of this is available. Also, second part is once we create those tools, where do we put them? And how can we share them with the community? So I developed this website called GRAND, Gene Regulatory Network Database. And that's a collection of networks for cell lines, tissues, and more than 20,000 drugs and chemical compounds. You can browse the networks here. So this is NetZoo, this is GRAND. You can find networks here, you can download them, access the data that was used to generate those networks, and also there is an API so you can access all this data programmatically. You can also do some analysis on the cloud without any necessarily knowledge of programming knowledge. Last but not least, so we need help. If you like this, if you like the tools, go on GitHub and give us a star. That would be really helpful for development of the tools. And also this website, brand.networkmedicine.org, is still at the test phase, so if you can have a look and tell me what functionalities before going to production that would be pretty
Does anyone have any questions for Marouen?
Could you give us some detailed explanation, more details to how your network is? Like you mentioned that it's bi-party, so could you give me more description on your network?
Yeah, so the network is a bi-party graph, and the nodes are regulators, proteins, called transcription factor, that affect the expression of genes. That's the other basic nodes. And the link here means regulation. And that edge could be binding the promoter region of the gene, or let's just consider that. And to reconstruct this network, we use different types of data, and then we try to find agreement between those different types of data to reconstruct this network.
Anyone else? Okay, thank you. And next up we have Jeff Miller, who's an assistant professor in the department.
All right, so I'm going to tell you about some of my research on Bayesian robustness to model with specification, and then some open problems that are yet to be solved, things that you might be interested in working on or thinking about working on. So for motivation for this work, the basic issue is that in Bayesian inference, in standard Bayesian inference, we assume that the model is correct. But unfortunately, even if there's a small violation of that assumption, sometimes that can have a big impact on your inferences. And there's a famous quote that all models are wrong, attributed to George Box. Another quote that I love is this one: "It ain't what you don't know that gets you into trouble. It's what you know for sure that just ain't so." And that is attributed to Mark Twain. And there's a story behind why I said it's not said by Mark Twain. I used to write that, and then a Nobel Prize winning economist, Lars Peter Hansen, in his talk took me down and said there's no way that Mark Twain actually said that. So I adjusted it to attribute it. But the basic point here is that if we do inference and we're very certain in our conclusions, then we better really be confident that they're correct. And unfortunately, oftentimes Bayesian posteriors will be very concentrated on things that later turn out to be not true. So here's an example to illustrate this in terms of inconsistencies that you get between the posterior distribution from the same model on different data from the same source. So this is from a paper that Jonathan Huggins and I are working on together. I don't know if he's here actually, but he spoke at the last lightning talks. So this is in phylogenetic inference, where you're trying to infer a phylogenetic tree among different organisms. The overlap that you get from different posterior distributions using the same model, so like this JC model, on two different splits of the data set. So this green dot is the first half of the data, and the red dot is the the green dot is the overlap between the first half of the data and the second half of the data. And there's zero overlap between those, like 99% confidence regions of the posterior. So that's a real problem. So it's self-contradictory. Here's another example where this is data from flow cytometry, and you would like to identify that there's 3 clusters here. But if you run a standard Bayesian mixture model, then you get a lot more clusters than 3. So this is due to some sensitivity of the model to the exact distribution of the data. All right, so there's lots of approaches that people have taken to try to be more robust, to misspecification of the model, or maybe a bad choice of prior. Some of the original work on this uses what's called minimax approaches in decision theory, which is to allow for some wiggle room in your assumptions. There's a lot of work on Bayesian non-parametric models. There's work in frequentist literature and Bayesian literature on generalized likelihoods. There's some more recent work on power posteriors where you weaken the likelihood by raising it to a power less than 1. And we have some work recently, so this paper with Jonathan is on what we call a bagged posterior, which is using Bootstrap to resample the data and average over a bunch of posteriors that are all plausible. So to illustrate that last one, this is a figure from our paper on that phylogenetic inference problem. If you use bootstrap aggregation, you generate a lot of bootstrap, non-parametric bootstraps of your data, you compute the posterior from each of them and average the results, then you get much more self-consistent results. So the overlap, like this green dot here, between the first half of the data and the second half of the data, the overlap of the posteriors you get is in the range of 30% rather than 0. So it's much more coherent. This is on that flow cytometry data. If you use a non-parametric algorithm, then you get something close to the manual ground truth. So there's lots of open problems in this work. By no means has all been solved. If you're interested in working on any of these things, I think I'm almost out of time, but please get in touch with me. I'm very interested in working on this, and I think there's a lot of exciting problems to be solved. So thanks for your attention.
You had 4 seconds. It's fair. I wanted to hear your sound, too. Does anyone have any questions? Yeah. All right. Thank you. And next up, we have Corbin Quick, who's also a postdoctoral research fellow in the department.
I'm Corbin. I'm a postdoc in Shihong Lin's lab. I'm going to talk about some work that we've been doing on integrated methods to help identify causal variants in GWAS. So genome-wide association studies are studies where we've collected genotype data from a large number of participants with the goal of identifying SNPs, which are positions in our genome that the nucleotide differs between different people that are associated with the trait of interest. The results are often summarized in Manhattan plots like this one, where the x-axis is the chromosomes are laid out, and the y-axis is minus log 10 p-values for the association between SNPs and trait. So the closer together SNPs are on a chromosome, the more likely alleles are to be inherited together, and it gives rise to very strong correlations to SNPs that are in close proximity, which is why there's these kind of skyscraper structures. So because of the correlations, it's difficult to tease out which variants are actually driving the signals. So one approach that's often used to address this challenge is Bayesian fine mapping, which is basically a spike slab model. So you have a trait Y, genotypes G, and then the causal effects are assumed to follow a spike slab prior. So you assume that there's a small subset of variants with non-zero effects, and that most variants have zero effects. When you do fine mapping, so you go, this is like zoomed into a Manhattan plot. Okay, so before, so you start with p-values for marginal associations, and you end up with posteriors, which tell you the probability that each variant is causal given the GWAS data. There's often a lot of uncertainty still because of the dense LD, so or correlations between SNPs. So one of the things we've been working on is incorporating annotations in this framework, which tell us about the functionality of SNPs. So there's kind of two two goals here. One is to help identify causal SNPs. It's thought that functional SNPs are more likely to have causal effects on traits, and then also identifying which annotations are relevant for the traits that we're studying. So the model setup for this is pretty simple. It's a lot like a logistic regression model, where each observation is a SNP, and the response variable is an indicator telling us which SNPs are causal. It's a little bit more tricky in that we don't observe the response, so we end up with this kind of funny-looking likelihood that accounts for the uncertainty in the response. So we've done simulations to check that everything checks out. This is looking at the calibration of posteriors, and these bottom plots are showing that in simulations incorporating annotations helps correctly identify causal variants. Real data applications, I've looked a lot at the GTEx data, which is gene expression measurements from about 25,000 genes across 50 tissues. So this is a data set we can use to identify SNPs that affect gene expression levels. And so applying this in real data, real data tends to be messier and more nuanced than simulated data. One kind of interesting problem that came up when looking at enrichment in real data was the TSS proximity. So as you get closer to transcription start sites, there tends to be a lot more regulatory features like open chromatin, more transcription factor binding sites. There's often also a lot more variants that affect gene expression, or geosis. So what happens if you look at enrichment for annotations one at a time, you kind of end up picking up a lot of yes, there's confounding. So the approach that we took here was to use a cubic spline for distance from transcription start site to pretty major effect on the enrichment estimate. So some other related work, working on more efficient approaches to account for relatedness and analysis, using the same weights to help boost power in gene-based analysis, and also looking at rare variants that affect gene expression levels. Yeah, that's the people.
Does anyone have any questions for Corbin?
Sure.
If you go back to your transcription size, there we go. Is that interesting periodicity got to do with the nucleosome occupancy perhaps? It looks like it occurs roughly in sort of 1-200 base pairs, right? Has that got something to do with the accessibility of the DNA because of nucleosomes?
That's a good question. I haven't looked into that, but that would be interesting to investigate further. I'm not totally sure.
Anyone else have any questions? Okay, thank you, Corbin. All right, sorry, it's a short week this week with 3 speakers, so stick around for the happy hour though.